Today we are going to go over the second part of 8.7, Taylor and Maclaurin polynomial approximation and the Lagrange error. So let's have a look at the warm-up problem here. Before we approximate fx equals 1 plus sine of x with the tangent line at 0 equals 1, which is y equals x plus 1. So at x equals 0, y equals 1, if we do the tangent line approximation, this is the tangent line approximation. So let's have a look. If we use second and third Maclaurin polynomial to approximate this function fx, which is 1 plus sine of x, what we will have? So Maclaurin series or Maclaurin polynomials, f of x is approximately equal to p2 of x or p3 of x. So we are going to do the second and third polynomial. So as we know, f of x equals p2 of x will be f0 plus derivative times x plus second derivative x squared third. Now we have to evaluate f of 0, f prime, and f double prime and triple prime. Given f of x equals 1 plus sine of x, f prime equals cosine of x. Now we just need to plug fx equals 0 in. So p2 of x in this case equals 1 plus x plus 0, the second squared, which is the second derivative 0, and p3 of x, which is 1 plus x, this becomes 0 plus 3 factorial x to the third, because the derivative is negative. So this is the second and third polynomial. If you look at the second degree Maclaurin polynomial, is exactly our line approximation. And the third degree, which is a higher order, which is a polynomial here. If you look at the picture, if you draw it, will be something like, which is more accurate than the line approximation. So before we go over the error bound, let's have a look at what we learned last time. We learned the Taylor and Maclaurin polynomial approximation. F of x is approximately nth term Taylor polynomial centered at C, and centered at 0, which we call the Maclaurin polynomial approximation when x equals when center C equals 0. And some of the notations are our vocabulary on the test. So we call the original function f of x, and the approximation which we use Pn of x or Tn of x. And when we look at center at equals 0, the approximating polynomial is set centered at 0. Or sometimes they use the word expanded about 0. And this polynomial is called Maclaurin polynomial. Otherwise, other than 0, any other center, we call it centered at C or expanded at C, which we call Taylor polynomial. As we mentioned before, every time when we approximate any function f of x is given by Pn of x. This is an approximation. So when we approximate, there will be an error here. So if you look at this equation, f of x equals fc plus here until here. This is Pn of x, our approximation. So fx, the exact function, original function, equals the Taylor polynomial Pn of x plus r of n of x, which we call the remainder. So similar to 8.5, f of x minus the difference between the approximation and the original function is given by the remainder, which is the function in this case. And the remainder is very similar to the next term here, which is n plus 1 term. The only difference right now, here we use another value z. This is called the Lagrange form of the remainder. And now let's have a look at what's the error bound. The remainder is bounded by some function. Let's have a look. Similar to the error bound for alternating series, when we use Taylor-Maclaurin polynomial approximation, we also have errors, and this error is called Lagrange error. And the Lagrange error bound, so the error equals the difference between original function and your approximation, which we call the remainder. The remainder is bounded less or equal than m times x minus c to the n plus 1 divided by n plus 1 factorial and absolute value here. Very similar to the next term. However, the letter m here, where m is the maximum value of the absolute value of the next n plus 1th term derivative of f on the closed interval between x and your center c. And we look at this function, n is the degree of the Taylor polynomial, which is the highest power of x, and c is our center, and x is the number you are trying to approximate. So let me write this sentence using the math equation. So the m equals the maximum value of the n plus 1 derivative of x on the interval between x and c, or c to x, depends on which value is bigger, where your x value is the one you are trying to approximate, c is your center. For example, if we approximate f of x centered at 0, approx fx at x equals 2, centered at 0 with third degree polynomial, then our maximum value will be maximum value next derivative, which is the fourth derivative of x. On the interval, because our center is 0, we are trying to approximate 2. Between 0 and 2, we are trying to find the maximum value. This will give us the m. Let me show you one example. Example 1, find the fourth degree Taylor polynomial for f of x equals cosine of x, centered. Okay, this is our center, pi over 4. And b, approximate cosine pi over 5. C, find the Lagrange error bound for your approximation. And d, what's a Lagrange error bound if we approximate cosine pi over 3. That said, before you do the problems, you better write the formula down first. So a, we are doing the Taylor polynomial, so Pn of x equals f of c plus c derivative at x plus c So now the center equals pi over 4, and we are doing the fourth degree Taylor polynomial. So we are looking for P4 of x, which is f pi over 4 plus derivative at pi over 4 times x minus pi over 4 plus f pi over 4 second derivative. To the fourth power. Now we have to evaluate f pi over 4. So given f of x equals cosine of x, derivative negative sign, now we just plug in pi over 4. cosine power 4 square root of 2 over 2. Power 4. Be careful, this is very tedious. Just be careful your calculation. So now we plug all the values in. So P4 of x equals f power 4 square root of 2 over 2 minus square root of 2 square root of 2 over 2 factorial over 2 divided by 2 factorial. You don't have to simplify it if you don't want to. To the fourth. So this is our fourth degree Taylor polynomial centered at power 4. B, we are trying to approximate cosine power 5. So we just call cosine power 5 will be approximately equal to all the x here will be replaced by power 5. Square root of 2 over 2 minus squared. Just replace everything using power 5. Now you can use our calculator, which is 0.809016. At least 4 decimals when you solve this AP type of problem. So this is our polynomial, and this is our approximation. So given this, let's have a look at part C. Find the Lagrange error bound for this approximation. So Lagrange error bound, as we know, is given by m times x minus c to the n plus 1 because we use the fourth degree, so it's 5 here. And c divided by 5 factorial. In this case, our center, x equals power 5 and the center equals power 4. We want to find the error bound here. The only thing right now we need to solve for the m here. As we know, m is the maximum value, the next derivative. The next derivative is f/5th derivative. On the interval from x to c, have power 5 to power 4. So the next derivative, the fourth derivative cosine the next derivative. Keep in mind absolute value of next derivative. So the maximum absolute value which gave us sine of x. So what's the maximum value on power 5 to power 4? You can use derivative or you can look at the graph. Sine from 0 to power 2 is here. So this maximum value will give us sine pi over 4, which is square root of 2 over 2. So this is m value. We are going to plug this m in. So it's square root of 2 over 2 times which is 5.635 times 10 to the negative 7. This is the error. The error is less or equal than this value, which is pretty good here. Let's look at part D. If we use this polynomial, same polynomial approximation to evaluate cosine power 3. So power 3, the only difference for the error bound is the m value. So x here, which is power 3, minus power 4. C center is power 4 over 5 factorial. So the maximum value, same thing, maximize sine of x. However, in this case, the boundary will be from pi over 4 to power 3. So because x in this case is power 3, center is power 4. So the maximum value will give us sine pi over 3, which is square root of 3 over 2. So the Lagrange error bound is given by square root of 3 over 2 times pi over 3 minus pi over 4 to the 5th power over 5 factorial, which is 8.875 times 10 to the negative 6. This is our x. This is our c. This is your x. This is your c. Okay, everybody, you can pause the video and have a look at example 2 and try to do it yourself and compare your answer with mine. This is the answer key for example 2, part A. Part B. Part C.